Okay, so in this unit, we are going to be talking a lot about exponent and their rules. So we're going to start today's lesson about 9.2 talking about exponent rules and properties that you learned in Algebra 1 and Algebra 2, and then we're going to move into something called rational exponents. Okay, so we're going to start with a review of exponent rules. So the first one, which we've used in class before, is the product rule. So if you have x to the a power times x to the b power, since they have the same base of x, we combine them with the same base and we add the two powers. If we have a quotient of the same base, so x to the a over divided by x to the b, we subtract the two. And we can also do something called the power rule. So if we have x to the a all raised to the b power, we multiply the two, x to the a times b. And we can also do the power of a product or quotient. So for example, we can have a to the x, actually that's not how I want to write it, but we'll do a to the x times b to the y, all raised to, I don't know, the c power. We can say that as a to the x times c times b to the y times c. You can distribute that power through, and you can do the same thing for quotients. So if we have a to the x over b to the y, all raised to the c, that's the same thing as saying a to the x times c over b to the y times c. So you can distribute the power to both the numerator and the denominator. So we're going to look at how to combine those exponent rules to simplify expressions as far as we can. So if we look at the one on the left first, we know that from order of operations, PEMDAS, we want to do inside the parentheses before we go outside the parentheses. So if I have inside the parentheses, I see that I have a 7, x to the 7 over x to the 2. So if I do 7 minus 2, that tells me I have 5 x's left, and they're in the numerator because I have more x's in the top than the bottom. Same thing for y. If I have 3 y's in the top but 1 in the bottom, I'm left with 2 total. And now I'm going to apply that 4 exponent to everything. So I distribute the 4 to both the 5 and the 2, and since I'm going to multiply, I'm going to get x to the 20th times y to the 8th, and that is the most simplified form that I can get because I can't combine non-like bases. So it gets a little bit more complicated when we go over here to the right-hand side of the board. So we want to look at both the fraction and the stuff in parentheses. So if I look inside this parentheses with 3xy squared, I can't do anything inside of that, so I'm going to ignore it for now. And I'm going to go look over at my fraction to the left. And we remember that this whole expression is over 1, so we know how to multiply. So if I look, I have 9 x's in the top and 6 in the bottom, which is going to leave me with 3 of them in the top. I have 3 x's in the bottom, 3 y's in the top and 7 in the bottom. So all 3 of mine in the numerator are going to go away, and I'm left with 4 y's in the bottom. I can't do anything with that 9 right now, so I can bring that on down. And then I have 1 z in the top and 4 in the bottom, so I'm going to get a total of 3 left in the bottom. And now I want to look at this fraction. So I'm going to put it over 1, so I have fraction times a fraction. So I'm going to distribute my power now to everything inside. So I'm going to have 3 cubed times x cubed times y to the 6th. And so I'm going to go off to the side now. I know 3 cubed is really 3 times 3 times 3. So I have 9 times 3, which is 27. So 3 cubed is 27. So I'm going to rewrite this, multiplying everything together. So I'm going to bring over my 27 right here. And then if I have x cubed times x cubed, I'm going to get 3 plus 3 here for my power, and a y to the 6th. 1 times my denominator in the bottom is going to give me 9 y to the 4th z cubed. And now I just want to see what I can simplify. So I have 27 over 9, so I can divide those, and I'm going to be left with 3 and 1. I know that 3 plus 3 is really 6, so I'm going to have a x power of 6. I have 6 y's in the top, but 4 in the bottom, so all 4 of my y's go away in the bottom, in the denominator, and I'm left with 2 in the top. So my final answer is going to be 3x to the 6th y squared all over z cubed. Okay, so we can also look at rational exponents, and rational just means a fraction. So when we're looking at fraction exponents, we can split them apart in 2 different ways. In the first one, we can pull the numerator value outside, and be left with 1 over n as the exponent on the inside, right? Because we know we're just splitting apart that fraction using multiplication. And we know from our discussion of nth roots in class that I can rewrite x to the 1 over n power as the nth root. So what this is really telling me to do is to take the nth root of x and then raise it to the m power. Or I can split it the other way. I can keep the numerator power in with the base, and I can bring the denominator power outside as a fraction. And again, we know that if we split that up using our nth root term, that is telling me to take the nth root of x to the m power. So we can use these rules to help us break down numbers without a calculator. So we're going to look at that with these two examples. So using that rule, I can split 64 to the 2/3 up in two different ways. I can either square the 64 first and then take the 1/3 power, or I can take the 1/3 power first and then square my answer. Not n, 2. Whoops. Okay, so if I don't know off the top of my head what 64 squared is, and we're doing this without a calculator, and I certainly don't want to do the longhand math, so I'm not going to do this method. But I do know that the 1/3 power is really the cube root of 64, and then I want to square the whole thing. Now, I know from the chart we made in class that 4 times 4 times 4 is 64, which means the third root of 64 is 4. So that's really going to be 4 squared, so my answer is going to be 16. We can do the same thing with other bases as well. So if I split this apart, I can either write it as 16 to the 1/4 power, all raised to the 5th, or I can write it as 16 to the 5th power, all raised to the 1/4. Normally it's easier to do the nth root first and then do the bigger power. So again, I'm not going to do this one because I don't know what 16 to the 5th power is off the top of my head. So if I'm looking at 16 to the 1/4 power, that's really the 4th root of 16, and I'm going to raise it to the 5th. Now, say I don't remember from the chart what that is. I can always go off to the side and break down 16. So 16 I know is 2 times 8, and then I can break 8 down into 2 times 4, and I can break 4 down into 2 times 2, which means that I can really write 16 as the product of all of the prime numbers at the end of the branches, if you remember prime factorization. So 16 is equal to 2 to the 4th, which means the 4th root of 16 is 2. So I know that this is really a 2, and we're going to do 2 to the 5th power. So that's 5 2s, so I know 4 2s is 16 times a 5th one, that's going to give me 32. We also have what's called a zero exponent rule and a negative exponent rule. So any number raised to the 0 power is always 1. So for example, 5 raised to the 0 is equal to 1. 1,000 raised to the 0 power is equal to 1. No matter what number you choose, any base raised to the 0 power is 1. And then we also have negative exponents. So what a negative exponent tells you is that it's in the wrong side of the fraction. It tells you to take the reciprocal of wherever it is. So for example, if I have 2 to the negative third, I can really put 2 over 1, and it tells me that the 2, the base of it, wants to be in the other side of the fraction. So I can rewrite that as 1 over 2 cubed. As soon as you move it to the opposite side, the exponent becomes positive. Another example would be if I had 1 over 4 to the negative 3 power. That's telling me the 4 doesn't really want to be in the denominator of the fraction, it wants to be in the numerator. So that would flip it up and be a 4 to the positive third over 1. So we can use that in combination with any of our other exponent rules. So if we're looking at 49 to the negative 3 over 2 power, that combines our negative exponent theorem with the rational exponent theorem that we just talked about on the previous slide. So because this is a negative exponent, it's telling me that this 49 does not want to be in the numerator of its fraction. So we're going to move it to the bottom, which means I'm going to have a 1 on top, and then I have 49 to the 3 over 2. So we know from our last slide discussion that the 2 in the bottom is what the nth root is. So this is really telling me that I want to take the square root of 49 and then cube it. Well, we know that the square root of 49 is 7, so I want to do 1 over 7 cubed. So that would be 7 times 7, which is 49, times another 7. So we'll just go off to the side and do some longhand math since this is non-calculator stuff. 9 times 7 is 63. Carry the 6. We have 4 times 7 is 28. 28 plus 6 is 34. So that means 7 cubed is 343. So my final answer is 1 over 343. Okay, so we're going to look at how to simplify expressions that kind of combine all of our rules. So if we look at our first example, we have some negative exponents in there. The first thing you always want to do is go ahead and move everything that has a negative exponent so that way you only have positive exponents to deal with. So because I have a fraction in my first term, I'm going to put the second term over 1 to remind me I have a fraction times a fraction. So I'm going to look at these things, these terms that have negative exponents, because those tell me that those specific bases want to be in the opposite side of our fraction. So I'm going to leave everything that has a positive exponent where it is. So in my numerator of the first term, my 2 and my s to the 6th are going to stay where they're at. My r cubed was already in the bottom, but I'm going to bring down that r to the 5th power and make it a positive exponent now that it's in the denominator, and I'm going to leave my s to the 4th alone. Same thing over here, I'm going to have 3r to the 6th, and then I'm going to have s to the 4th in the denominator because that s had a negative 4 in the numerator. So then we're just going to multiply our fractions and combine any like terms we have. So 2 times 3 is 6. In the numerator, I don't have any like bases, so I can't simplify their exponents. Oh, sorry, that's not a 6, that's a 9. Whoops. And then in the bottom, I have r cubed times r to the 5th, so that's r to the 8th, adding their powers together. S to the 4th times s to the 4th would give me s to the 8th by adding those powers together. And then I'm just going to go ahead and simplify any powers between my numerator and denominator. So I have 6 x's in the top, but I have 8 in the bottom, which is going to leave me with a total of 2. I have 8 r's in the bottom, but 9 in the top, so I'm going to have 1 left over. So my final answer here is going to be 6r over s squared. Moving on to example number 2, we want to do the same thing. So if we look, we have a lot of different negative exponents in here. The negative exponents only move what they are directly touching. So over here in my first term, my 3 and my m cubed are going to stay in the numerator of this fraction, but my l squared is going to go to the bottom because it had a negative base. And the negative 2 there was only touching the l, so that's why the l is the only thing that moves. In the second fraction, it's all still going to be squared on the outside, but on the inside, that m base has a negative 5 exponent, so it moves to the bottom. But the 2 stays in the numerator because that negative 5 is not applying to the 2. Over here, however, we have a negative 3 exponent on the whole thing, which tells me I want to flip the whole thing upside down. So I'm going to have a 1 in the top, and I'm going to raise L m to the 4th all to the positive 3rd power in my denominator. So now I'm going to go through and simplify anything that I can. So I first need to deal with these powers that are on the outside before I can combine any of my fractions together. So I'm going to leave 3m cubed over l squared alone. If I square the whole second term, I have 2 squared, which is 4. M to the 5th squared is m to the 10th. I have nothing applying to my 1 in the numerator of the last term, and if I distribute that 3 power, I have L cubed m to the 12th. So now I'm going to combine them all together by multiplying. So I have no other numbers in my numerator except for 3 and 4. 3 times 4 is going to give me 12. And then m cubed is by itself in the top. If I look in my denominator, I have L squared and L cubed, so I have a total of L to the 5th. And then I have m to the 10th and m to the 12th, so I have m to the 22nd power. Again, we want to simplify anything we can. I have a 3 and 22, so all 3 of my m's in the numerator are going to cancel and leave me with 19 in the bottom. So my final answer here is going to be 12 over L to the 5th times m to the 19th power. And then, of course, we can always go ahead and apply our negative and rational exponents at the same time. So another example of this, that negative is on the base 81, so the whole thing is going into the denominator. And this tells me that I want to take the 4th root of 81 and then cube the whole thing. So I need a number multiplied by itself 4 times to equal 81. Well, that's going to be 3, so this is really 1 over 3 cubed. But 3 cubed is 3 times 3 times 3, which is 27, so my final answer is 1 over 27. Okay, here is your set of OYO questions. You want to take a second to pause the video and write them down and simplify them onto your note sheet and make sure to show all of your work.